Hello, welcome to this inaugural presentation. I'm very happy to present my work to you. In my work, I develop mathematical theory for dynamical systems. These are mathematical objects which are used to model many kinds of natural phenomena like fluid flows, temperature diffusion, waves and vibrations, and elastic deformations. In my work, I'm interested in the fundamental properties of these models, but also in developing ways to influence their behavior by so-called control actions. And I'll begin by illustrating what I mean by control in this context. So one dynamical system that many of us are familiar with is just an ordinary car. It has many dynamical properties related to its motion, and one of them is the speed of the car. And this is something that we can measure out of our dynamical system. On the other hand, while we drive, we can and of course should also control the speed of the car by adjusting the action of the gas pedal. And if we are interested in maintaining the speed of the car at a constant level, we can either do this by manually adjusting the gas pedal, or alternatively we can use cruise control, which is exactly designed to help us achieve this goal. And the cruise control is an automatic controller which uses the speed of the car to adjust automatically the gas pedal. And in fact, this controller, the cruise control, works because of some fundamental mathematical principles. And in my work, instead of controlling a car, we're interested in controlling a mathematical model. Again, this model has some dynamical properties, and we can measure some quantities out of this system. And in addition, again, we have some dedicated ways of influencing the behavior of this model. And in our work, we're often interested in designing and developing these automatic controller mechanisms, just like the cruise control, which help us decide what kind of control inputs we should use in order to make our measurements behave in a desired way. One relevant question that comes to mind is, why do we control a mathematical model? Why not just control a car or anything we may eventually want to control? One of the principal advantages of this approach is that we get universality with mathematics. So control comes in many different forms. On the left here we have the so-called nano tweezers, which are like very miniature tweezers which can be used to grip individual DNA molecules from within cells and move them around. And because of their very small size, these tweezers are really flexible, and that's why they're difficult to maneuver precisely, and this is why we need controller design development. On the other hand, on the right, we have a large-scale robotic manipulator attached to a space station. And again, we would like to control the motion of this robotic arm, but now, due to the very large size of this structure, it becomes flexible, and that's why accurate motion is difficult to achieve. But from the mathematical perspective, both of these equations are modeled largely by a similar type of model, namely the beam equation. And this means that if we learn to control one of these models in the mathematical domain, this also teaches us something about how we could achieve better control for the other other kind of system, the other system. And in our research work in our group, we're interested especially on these flexible type of systems, but in addition with different kinds of phenomena like velocity, controlling the velocity and temperatures of fluid flows, and controlling waves and vibrations, let's say in acoustic environments or structures. And you may also wonder what this stylistic Newcastle Bridge does here in the slides. What is its role? Because it seems like a very solid and robust structure. But it's good to remember that even larger structures have their own dynamics, and understanding and being able to control these dynamics can have a dramatic effect on the durability of these structures. Now I could also spend a little bit of time talking about mathematics research in more general. So mathematics is a very wide field and it can be subdivided in many ways. But one of the ways that I like to think about its research is that it partly resembles archaeology and partly resembles architecture or visual arts. So in one of these parts, we are digging deep into the body of existing mathematics, something that came before us, and our aim is to uncover some hidden truths and yet unknown things about what has done before. On the other hand, part of the work is just about creating new mathematics out of simpler building blocks. This may be just for the sake of the beauty of the creating mathematics, or it could be about developing new mathematics to solve some problem from another field of science. But in any case, in this part, we take existing smaller pieces of mathematics and put them together, just like we would use Lego blocks to build something more interesting and complicated. And mathematics also is familiar with many misconceptions that I could maybe highlight here. So mathematics is seen as a very difficult field, but from my personal experience, I would say that it's no more difficult than any other field of science. Part of the seeming difficulty can be caused by the fact that mathematics has its own language, but this is on the other hand also true with any other field of science as well. But mathematics goes a bit further because we also express our language with our own alphabet, and this definitely steepens the learning curve of mathematics in the start. But nevertheless, my take-home message here is that this language and alphabet is something that anyone has the capacity to learn, provided that they have the proper motivation and put in some of the effort, and then they can start creating mathematics by themselves as well. The other thing is that you certainly don't need to be a genius to be a mathematician. Sure, in popular culture and in the news we learn about these mathematical geniuses whose great big inventions make the news and change the world. But underneath this tip of the iceberg, countless mathematicians are coming up with small mathematical inventions that are equally important every day. And all of this work underneath the surface contributes to the growth of mathematics. And our field this way has a lot of room for various types of researchers with different roles. Here you can think of an analogy coming from construction engineering, because we may say that probably the person who designed the Eiffel Tower had to be a genius, but the actual construction of the tower required a huge collaborative effort from a really big group of different people working in different areas of construction and engineering, and it is also only this group effort that resulted in the building we see today. To close my talk, I could also tell you a story of my day-to-day mathematics research life, maybe to dispel some of the glamour in it. So just a month ago, I was working on a problem that was supposed to be relatively easy to solve, and I could get a nice publication out of this. But while most of the work went really smoothly, I at some point noticed that there's this kind of a sub-problem that I really need to solve. And I quickly realized that this reduces to something quite elementary, just something about angles between vectors in a two-dimensional coordinate plane. And I thought that, okay, this at least has to have a solution, and I'm going to find it. But for the next 3 days, my whiteboard looked like different versions of this, with different kinds of very sophisticated and more complex ways of attempting to solve this problem, and I was filling in sheet after paper. And this didn't result in anything until waking up relatively early one morning. I decided to try something quite simple, and namely the simplest thing I could think of. And this happened to work, and the whole problem was solved by these 2.5 lines that you see here in front of you. Of course, I haven't told you anything about what this notation here means, but I bet that if I had 5 minutes more of your time, I could explain the problem and its solution in a way that everyone in the audience could understand it. I'll let you decide what are all the morals of this story. It could be about not making things too complicated and keeping it simple, or it could be about perseverance paying off. But to me, one of the key points is that it's sometimes dangerous to do mathematics just in isolation by yourself. And this is the reason why I'm really grateful for the opportunity to have such a nice research group here in Tampere, with many talented and really nice members. And I'm also thankful for all the collaborators and co-authors that I've had the chance to work with until this day. And with these thoughts, I'd also like to thank you for listening.